Welcome students, I am Dr. Ramesh Babu, Principal, Professor, Department of CSE, Sai Vidya Institute of Technology, Bengaluru. Today, we shall discuss on the instruction set of 8086. The agenda for the day, as per the syllabus of VTU, it is module 2, where we will be discussing on the instructions and its descriptions. Particularly, we will be concentrating on arithmetic and logical instructions and programs related to arithmetic and logical instructions, and we will end up this module with discussion on interrupt number 21H, interrupt number 10H and related programming. We also discuss on the interrupt structure of 8086, how does 8086 handles instruction, what is the need of instruction, how important is interrupt say for any 8086 processor or any processor as such, is what is the total agenda that we are going to discuss in module 2. At the end of this module, you would be able to write programs using the instructions of 8086. What are all the different types of instructions that is supported by 8086? 8086 instructions can be categorized as data transfer instructions, arithmetic instructions, logical instructions, group control instructions or branch group instructions, and machine control instructions. Now, we can categorize our 8086 instructions into 5 different classifications or types or categories. In the last module, you might have discussed about the addressing modes. Now, how do we correlate? What is the relationship between the addressing modes and the instruction set? My dear students, every instruction that you write in your program will use one or the other instruction addressing mode, or in other words, say all the instructions that you write in your program uses one or the other addressing modes. Now, let us directly get into the first type of instruction, what is called as data transfer instructions. We have more than totally 112 instructions in 8086 instruction set. Since there is a huge amount of instructions to be discussed, I will be taking you through with a quick approach for this data transfer instructions, which is very self-explanatory. The general structure of a data transfer instruction is as follows: move operand 1 comma operand 2, where both the operands cannot be memory. Only source operand can be specified by the immediate mode. You have learnt about immediate addressing mode. So, what I am trying to tell you is, say your source operand can be an immediate operand, your destination operand cannot be an immediate operand. When the source is immediate data, the destination can be either a register or it could be a memory location. When the source is immediate data, the destination can't be a segment register. Following is the example for a data transfer operation. Move OPR1 comma OPR2, where OPR1 is operand 1, OPR2 is operand 2, where operand 2 acts as source, operand 1 acts as destination. This particular instruction transfers, it copies the data from source operand, that is operand 2 to operand 1. The picture indicates that the data from operand 2 goes to operand 1. In fact, the instruction says is move, but it is nothing but copy. Let me get into the instruction directly. The very widely used data transfer instructions, say the first category is move register comma register, say where I have taken an example of move AX comma BX. This instruction moves the content of register BX to register AX. Now, if I ask you a question, say what addressing mode does this instruction is using, say probably you should be able to say that, sir, this is a register addressing mode based instruction. The reason is both the operands are registers, because the source operand and the destination operand are registers. Since the source and destination operands are registers, so it is a register addressing mode based instruction. Now, how does it works? The contents present in BX gets copied onto AX. So before execution, let me give you an illustration. Assume that the content of AX is 1, 2, 3, 4 and content of BX is 5, 6, 7, 8H. You know that AX is a 16-bit register and BX is a 16-bit register, where both of them holds a 16-bit data. Now, after executing move AX comma BX instruction, say the content of AX will be 1, 2, 3, 4, contents of BX will be 5, 6, 7, 8. No, the content of AX will be 5, 6, 7, 8, the content of BX will be 5, 6, 7, 8. If you carefully observe, a copy from the source, say the copy of the data from the source is say sent to the destination. Now BX had 5, 6, 7, 8, a copy of the data present in the source operand is being copied to the destination operand. In this case, the destination operand is AX. So the content of AX, say after execution of move AX comma BX instruction, is 5, 6, 7, 8. So you should never forget, move generally in our normal grammatical meaning of move is transferring, but here say we transfer but in terms of copy. Another data transfer instruction is move AX comma contents of BX. Now the difference between the first instruction and the second instruction is, in the first instruction I have used move AX comma BX, where both the operands were present in the register, but here one operand is present in the register, another operand is present in the memory. This instruction transfers 2 bytes of data from the data segment, say where from the data segment the data gets copied onto AX register. The register BX does not contain the data, the register BX contains the offset address. It is something like this. The value present in BX, the offset value present in BX is added with DS, where it gives me a physical address. The content of that physical address will be copied onto 16-bit register AX. Now, how does this basically works? Assume that AX has got 5, 6, 7, 8, BX has got 7, 3, 4, 4. Now, before execution, say DS has got 2000 and the content of say data segment, let it be something like this: 99, 77, 88, 55 and 56 is what is the say snapshot that I have taken from the data segment memory. Now, you know that the physical address calculation needs some conversion. I have the segment base in the segment register. My segment register is 16-bit, but my physical address is 20-bit. To convert the 16-bit segment base into a 20-bit segment base, what do you mean by segment base? Segment base is nothing but the starting address of the segment. So internally the address adder multiplies with this number by 10H. So ultimately I get 20,000H. Now this 20,000H will be added with the offset value given by BX. What is the offset value given by BX? It is 7344, where after adding these two, I'll get a physical address 27344H. H means hexadecimal number. Now, after execution of this instruction, what will happen? Now carefully observe. The contents of memory location 27344H will be copied to AX. Now if you carefully check the picture, so here what is happening? Content of 27344H content of 27345H is copied onto AL and AH, where the data from the higher memory location goes to higher byte of the register, that is AH, and the data from the lower memory location goes to the lower byte of, say, AX, that is AL. Now if you carefully observe here, say 44 is the lower address, so 99 will go to AL, 45 is the higher address, then the contents of this higher memory location, which is 77, goes and sits in AH. Now, how basically this physical address calculation happens? This picture illustrates the calculation of the physical address. My dear students, this is one of the speciality of 8086, where I have a 16-bit segment base, I have a 16-bit offset. Using a 16-bit segment base and a 16-bit offset, I would be able to calculate a physical address which is of 20-bit. But however, before calculating the physical address, the segment base present in the segment register, in this case the segment base is given by the data segment register, say, which will be multiplied. Now the segment base is 2000, so that will be multiplied by 10, so which gives me a segment address or a segment base, for which I will add the offset. The offset is 7344H. So after adding this offset to the obtained 20-bit starting address, I will get the actual physical address at which my data is stored. You already know this, that 8086 is a 16-bit microprocessor, where whenever it transmits a data, say from memory, or it receives the data from the memory, always it handles 16-bit data, say, into or from the memory. So that is the reason why in the data segment memory I am trying to show you that two memory locations are being considered. One is 27344H, another one is 27345H. So contents of these two memory location, which gives me a word data, and this word data will get copied onto the destination register. Say in this case it is AX. My dear students, please remember, memory is byte oriented. What do you mean by memory is byte oriented? Every memory location accommodates 8-bit of data. So if I am trying to receive 16-bit of data from the memory, then that 16-bit of data from the memory comes from two consecutive memory location. Now what if I am receiving 32-bit data from the memory? If I am receiving 32-bit data from the memory, or if I am writing 32-bit data to the memory, it always works with 4 consecutive memory locations, where every memory location accommodates 8 bits of data, that is 1 byte of data. So 32 bits consists of totally 4 bytes of data. So 4 memory location is what is considered. So that is how basically your data transfer operation with memory works. However, in 8086, since it is a 16-bit processor, the data handling with the memory generally happens 16-bit at a time. Another example, move AX, 36H. What kind of addressing mode based instruction is this? Since you have an immediate data, what is that immediate data in this instruction? 36H is an immediate data in this instruction. I have already mentioned it very clearly that your immediate operand can only act as source operand and it cannot act as destination operands. That is a rule that need to be followed, say, when you are trying to write 8086 instructions in your program. Now this instruction transfers the given data in the instruction to the specified register. The data itself appears as the second operand in the instruction, where it is called as immediate operand, where your 36H gets copied onto AX. Now before execution, AX content is 1234H, and after execution, AX content is, say, instead of 1234H, it gets copied to 0036H. Now what is the meaning of this? So the value 36H gets copied onto, say, AX in like 0036. 36H. So an immediate data gets copied onto AX in this instruction. Since I am using an immediate operand in my instruction, this instruction falls to the category of immediate addressing mode based instruction. Another instruction, move AX comma 34H, contents of BX and contents of SI. Now, the first question that comes to your mind is, sir, already we know how to access data from the memory. In the previous instruction, move AX comma contents of BX, where contents of BX means BX is pointing to some memory location, content of that memory location is copied onto AX. So I know how to access data from the memory location. Then why do I need one more instruction where I have the effective address given by 3 components? Because this square braces clearly indicates that, say, they are acting as a memory pointers where they do not have the data, they give the offset address. Let us try to understand how it works. This instruction transfers the data from memory to AX register. The effective address of the memory is the sum of BX and SI contents, and then the displacement 34H is also added. It means that you have totally 3 components in calculating the effective address or the offset. The data segment register, that is the DS register, is used for calculating the physical address. Remember, always your data will be either present in data segment, or it could be present in the extra segment, or it could be present in stack segment if you have stored the data in the stack. In a normal general case scenarios, your data will always be stored in the data segment. Obviously, I will be using, or 8086 processor will be using data segment register in calculating the physical address. Now, how does the physical address is calculated here? The content of DS is converted into 20-bit, and then it will be added with, say, BX plus SI plus 34, where contents of BX plus SI plus 34 will give me an offset. This offset is added with the segment base, which gives me a physical address. From that physical address, I copy the contents of those physical memory locations onto AX. Now, how does this work? Let us try to understand with a picture here. Now, the content of SI, let us assume that it is 336X. The content of AX is 5678. The content of BX is 7344. The content of DS, let us take it as 2000H. And I have just taken a section of data segment memory. Now, before execution, this is what is the content of my registers and the data segment memory. Now, once this instruction starts getting executed, immediately the data segment register content is taken, multiplied by 10 to convert this 16-bit starting address of the segment into a 20-bit starting address of the segment. Who will do this? The address adder, which you have seen in the architecture of 8086, does this job. In the bus interface unit, if you carefully observe, there is a box called as address adder. So that address adder does the job of doing all this conversion process. Now, for this 20-bit segment base or the starting address of a segment, I will add the offset address from, say, different registers, that is contents of SI, contents of BX, and then the immediate displacement, that is 34H, is added. So ultimately I get 2A6DEH as my physical address. Now, on the right hand side, you have the scenario how it will be after execution of this particular instruction, move AX comma 34H of BX of SI. Now, the physical address obtained is 2A6DEH. The contents of 2A6DEH and 2A6DFH will be copied onto the destination register, that is AX. Currently, AX has got 5678H. After execution of this instruction, the contents of these two memory location goes and sits in AX. Now, after execution of this instruction, what is the content of AX? The content of AX is 7799H. My dear students, if you carefully observe these two memory location, as I iterated, say, the contents of the lower address, which is the lower address here, 2A6D E is the lower address. The content of lower address goes and sits in the lower byte of the register, destination register. The content of the higher address, that is 2A6DF in this case, which is 77, goes and sits in higher byte of the destination register, that is AH of AX in this particular case. Now, why do we use this complicated instruction? Because I am trying to calculate the offset using three components, one base register, one index register, and an immediate displacement. Why do I need this? This clearly indicates when I am trying to handle a two-dimensional array like matrices or array of structures, I need an addressing mode to handle such type of data. To handle such type of data, I go for these type of instructions. Now, how basically the physical address gets calculated? The content of DS is multiplied by 10, which gives me a segment address, and that segment address is added with this index register and the base register as per the instruction, and then 34H is the immediate displacement which gets added to this, which gives me the offset, and this offset will be added to the segment address, where after adding the segment address and the offset, I get the physical address. Now, who will do this job? All this job will be done by the address adder in the bus interface unit. Never forget, bus interface unit acts as an interface between the processor and the outside world. So, whenever processor wants to access the memory, the address calculation follows the same principle of taking the segment address from the corresponding segment register, say of the target segment being accessed, and then for which an offset will be added. However, before adding the offset, the segment base address, which is a 16-bit address present in the segment register, gets converted into 20-bit segment address by multiplying it by 10, and then the offset is added so that I get the physical address. Now, see, this offset is also called as an effective address. The next instruction is LEA, load effective address, LEA, load effective address of operand 1 or operand to the destination register. Here, the OPR, that is operand, can be represented using any of the addressing mode, where say we will be using a memory operand here. The destination can be represented by any 16-bit register of the microprocessor. How does it work? This instruction transfers the effective address or the offset address of the source operand, and the same is transferred to the specified destination register. This instruction does not calculate the physical address. Only the effective address or the offset address is copied onto the destination register, which is used in the LEA instruction, say that is LEA destination comma or dest comma OPR. This instruction does not transfer the data. The name itself says load the effective address of the operand, memory operand given in the source position to the destination register. Let us try to understand this with an example. LEA BX comma contents of BP plus DI. My dear students, when you see a square braces, please remember that this square braces indicates that you are trying to operate with a memory operand. Now, let me take an example. See this, move AX comma BX, move AX comma content of BX. Now, once you see this square brace, it indicates that the square bracket indicates that I am not copying the contents present in BX. I am interested in the contents of the memory location pointed by BX. You are all computer science and information science students, you understand pointer concept better. So I can say that this acts as an index. What is meant by index? Index is nothing but pointer. So here bx does not hold the data, bx holds the address of the data, where say from the address of that memory location, from that memory location address, I copy the content and then transfer it on to AX. Now here also in LEA BX comma contents of BP plus DI, the sum of BP and DI register contents is the effective address and it is transferred to BX register. Now BP plus DI, contents of this BP plus DI is copied to BX. Say, how does this works? Now let us try to understand. Before execution, the contents of BX is 1234H, contents of BP is 5678H, and content of DI is 3569H. Now initially we'll add BP plus DI. BP is 5678 and DI is 3569H. Both of these are added. I will get 8B EH. So 8B, say E1H, and then after the execution, what will happen? Say, let us try to understand now. Whatever the effective address that I have got, what do you mean by this effective address? When do we use this? Say, this effective address is an address of an memory operand or a memory data present in that particular memory location. So the offset address of that particular data present in the memory would be copied onto BX. Now BX was 1234. Now BX is 8B E1H. 8B E1H. Now say after adding these two, whatever the value that I get is copied onto BX, and this in turn gets added with say DS and then processed further. Next instruction is a very special instruction. Carefully observe this. LDS destination comma operand. The OPR or the operand can be represented using any addressing modes of the memory. It could be direct addressing mode, it could be indirect addressing mode, it could be index addressing mode, it could be base addressing mode, base index addressing mode. You can use any of the memory addressing modes. The destination can be represented by any 16-bit register of the microprocessor. How does it works? The instruction transfers totally 32-bit data from the memory. Carefully observe this. It transfers 32-bit data from the memory. The first 16-bit of data from the memory will be copied onto the specified destination register, which is mentioned in the instruction, and another 16-bit from next memory location is transferred to DS register. So the data which will be transferred from the location is 32-bit. First 16-bit goes to the destination register, next 16-bit goes to the DS register. Now let us try to understand how basically this instruction works. Now say here the content of DS is added with content of DI. I get a particular memory location. So content of those memory location is copied onto BX. Then for the same obtained memory address, I will add +2 because this is a 16-bit data transfer. So that the pointer has to be incremented by 2. I will add +2 and the content of next two memory location will be copied onto data segment register. Now how does this work? I hope this animation would help you to understand the instruction better. Say, let me go through this animation. LDS BX comma DI. What is the BX content? BX content is 1234. What is DI content? 5678H. What is DS content? DS content is 9000. Now, as usual, the segment register content shall be multiplied by 10H. Say, why should I multiply by 10H? Say, this has to be multiplied by 10H, say, to convert this into 20-bit physical address. Who does this? I am not doing this. Means the programmer doesn't do this. Internally, the bus interface unit, say, has got an address adder which does this job. Now for this 20-bit segment base, the offset from DI is added, that is 5678, I get a physical address, and the physical address obtained is 95678. Now, from memory location 95678 and 95679, I would be able to take the data. Now carefully observe this. From 95678 say and 95679, the data is copied onto say BX register, that is 5645H. 5645 is copied onto BX. Then from next to memory location, the data gets copied onto DS. Now DS earlier was 9000, but now DS is 9A78H and BX is 5645H. Now if I add these two, I get a different physical address in the existing data segment, or it could be in some other data segment. Now the question that comes to your mind is, sir, why do I need this? In what applications, in what scenarios I would be using this particular instruction? My dear students, when you have some predefined table stored at a predefined location, you are aware of that predefined location, memory location addresses, where in your program you want to use that table for some conversion purpose. So, or you wanted to use that table for some access, or you want to access that for some purpose. In that case, say I can convert the value or change the value of data segment say to the say base address of the new data segment at which the table is present, and BX will be pointing to the starting address or to the appropriate location of that particular table, and that is how basically LDS BX comma DI works. Now this picture illustrates how your physical address calculation happens. Say you should never forget a very important concept. Even in the examination they'll ask you, say how does say the content of data segment or any segment register say gets converted into 20-bit address, and then you calculate the physical address. You may get some numericals where they give you the segment register contents, they give you some offsets in the different registers, and then say they will ask you to calculate the physical address. Like LDS, we also have LES. LES, destination comma operand, where the operand can be represented say using any addressing modes of memory. The destination can be represented by any 16-bit register of the microprocessor. How does it work? As usual, the instruction transfers 32-bit data from the memory, where the first 16-bit data from the memory goes to the specified destination register, and the next 16-bit goes to the ES register. Now see this working functionality. Now say the contents of the memory location obtained by adding DS with DI goes to BX, and the contents of memory location obtained by adding DS with DI plus 2 goes to say ES register. Now let us try to understand how basically this works using this animation. Now before execution, say what is my scenario? My scenario is say BX has got 1, 2, 3, 4, ES has got 2, 2, 3, 3, and DI has got 5, 6, 7, 8, and DS is 9000. Now this segment base is taken, multiplied with 10H, I get 90,000. When you multiply 9000 by 10, I get 90,000. Now one commonality, I don't know whether you observed this or not. Every time when I calculate the physical address, have you observed that the last nibble is always a 0? Yes, of course. There is a rule in 8086 where every segment will start with the last nibble as a 0. Otherwise, appending this last 4-bit for this upper 16-bit is next to impossible. So we will have the upper 16 bit of the starting address of any segment in the segment register, and for that upper 16 bit of starting address, when we try to multiply that with 10, that is address adder multiplies it by 10, so that this gets converted into a 20 bit starting address. Now this 20 bit segment base, I call it a segment base or starting address of the segment, will be added with the offset address. Here the offset address is given by DI. What is the content of DI? 5678H. When I add this, I'll get 95678. So the target memory address is 95678, and from that memory location, say we take the data and copy that onto BX. So BX contents are filled from say 95768 and 95679 memory location, and for ES I take the data from 9567A and then 9567B, say as shown in this figure. Now ES earlier was having 2233H, but now say ES has got 9A78H. When you add ES with say now BX, so it will point to a new segment location at which you have some predefined data stored say in that particular memory location. Now how does physical address is calculated? Offset is added with the segment base. Before adding the offset to the segment base, it has to be multiplied by 10, so that you get a segment address or the starting address of the segment, or we can call it as the segment base address, say for which offset is added, then I get a physical address. And this particular process is very important with respect to examination point of view is concerned, and with respect to programming point of view is concerned, because say this is a fundamental aspect of say programming. Another simple instruction, exchange operand 1 with operand 2. How does this instruction works? Operand 1 and operand 2 can be represented by any one of the addressing mode except the immediate addressing mode. So exchange is an instruction where it doesn't allow an immediate operand to be used, because immediate operand is nothing but a constant, it is a literal, so I will not be able to exchange it with either a register or with a say memory. So it could be a memory or a register, but however both operands cannot be memory. So in 8086 we have a limitation where say we don't use two memory operands in single instructions. Both operands must be of the same size. You cannot have one operand as 16 bit, another operand as 8 bit. Now this is a common doubt that majority of the students will have. Say for example, say I have an instruction move AX comma AL. Now the student will have a doubt, sir, AL is 8 bit, sir, or I will say BL. I will say BL. Sir, BL is 8 bit. The content of BL is 40, sir. Now AX is 16 bit, which has got AH and AL. So as per this instruction, sir, this is source is 8 bit, destination is 16 bit. Sir, this should be possible. Could be a question in your mind. But unfortunately, your processor cannot do this even though the destination is bigger than the source operand. The reason is, say it is an ambiguous instruction. Your processor would not be knowing whether to copy this to BL or copy this to say copy this to AL or to copy this to AH. If you ask me a question again as an hypothetical say imagination or whatever it may be, sir, say BL should go to AL, no sir, say why, what is the problem here? No, nowhere we have said say always lower bytes works with the lower byte and higher byte with the works with the higher byte. Say for example, say instruction like move AH comma BL works fantastically fine, move say AL comma CH works fantastically fine. When we handle these registers as 8-bit registers, they work independently. They work as an independent 8-bit entity. So here both the operands must be of the same size. However, I need not have to tell you, you cannot have something like, say, this is ruled out. Say the reason is the source is 16-bit, but the destination is 8-bit. You cannot copy a 16-bit data to an 8-bit, say, destination. Say, as simple as that. Now, both the operands must of the same size, and this is common to all the instruction, not only for exchange. This instruction will exchange the data present in two operands. How does it works? Now, carefully see this. Say, before execution, BX has got 1, 2, 3, 4, CX has got 5, 6, 7, 8. Now, after the execution of this instruction, so BX will have 5, 6, 7, 8 and CX will have 1, 2, 3, 4. So, exchange is mere copying of, say, source to destination and destination to source. So, this picture depicts how basically exchange, say, instruction works. XLAT, very important instruction. XLAT is called as translate. It is nothing but translate instruction, where in this instruction the operands are not specified explicitly, but they are implied, they are understood. This instruction transfers 1 byte of data from the data segment memory to AL register, where the offset address is calculated as sum of the contents of AL register to BX register. It is nothing but AL will be copied with the contents of memory location obtained by adding DS with the offset address BX plus AL. Now, what do you mean by the operands are implied here? In this instruction, I have not specified any operands. Then say, what should I do? The programmer should load the appropriate value to AL and the appropriate value to BX. Say, in this case, basically we use translate instruction for converting the content of BL into its equivalent form. Assume that you have a data, a BCD number in AL, you want to convert that into an ASCII value, and in your program, if you do this operation very repeatedly, there is no point in, say, writing code for that. We can create a table, ASCII table in the data segment and load the starting address of that particular ASCII table in BX, and say before using XLAT instruction, you should be able to load AL with the value to be converted. So, if AL has got 3, say after execution of this instruction, AL will have 33, where 33 is the ASCII value for 3. So, for such kind of translation, we use XLAT, a very important, very peculiar and special instruction in 8086 instruction set. Now, let us try to understand how basically this works. Before the execution, BX has got 1, 2, 3, 4H, AL has got 78H, DS has got 9000H. As usual, the contents of data segment register, that is DS, is multiplied by 10, and then we get a physical address which is the starting address of the segment, for which the contents of BX is added. Now, it is the duty of the programmer to load BX with an appropriate value. As I said, say BX will generally, say, hold the starting address of the table or a translation table which is used to translate the content of AL to its equivalent value from the table. Now, in this case, say BX value is 1, 2, 3, 4H, say for which 78 is added, ultimately I get 912ACH. So, after calculation of the physical address, the content of 912ACH, which is 45, will be copied onto AL. If you carefully observe, say initially before execution the content of AL was 78H, and after execution the content of AL is 45H. So, this is what is translation. So, the content of AL gets translated into its equivalent value from the table say, or from a predefined location which is pointed by, where base address is pointed by the BX register. This is how basically the physical address is calculated, where the segment base multiplied by 10, starting address of the segment I get, say, for which the offset is added. Offset is obtained by two components, one is BX and AL. After adding these two, I get an offset that will be added with the segment address or the starting address of the segment to obtain the physical address. Now we have discussed the instructions which are pertaining to the data transfer, where we are transferring data from, say, data segment to, say, any register, or from one location to another location, or whatever it may be. Now let us get into another set of data transfer instruction, what is called as stack related instructions. What is the stack related instructions? A part of the RAM which is used as a stack. You know that stack is LIFO structure. It is a set of memory location which works in LIFO manner. So here also we have something called as stack segment, where the size of, maximum size of the stack segment is 64 kilobyte. Obviously when I say stack, it works in LIFO manner. So here a part of RAM will be considered as stack. Stack is part of the memory used for temporary storage of the data. The process of transferring data to the stack is what is called as push operation. When the data is transferred from the stack, it is called as pop operation. So two operations that we can perform on stack is what is called as push and pop. The stack pointer, it is a 16-bit register which we have discussed in the architecture of 8086, which is present in the register set of 8086. SP will always point to top of the stack. It is a 16-bit register which only works with the stack segment, and it will be pointing to the top of the stack. With every push operation, SP contents gets decremented by 2, and for every pop operation, SP contents gets incremented by 2. My dear students, remember, when I transfer data to the stack, when I receive data from the stack, I always work with 16-bit data. Either I push 16-bit data onto the stack, where stack pointer gets decremented by 2, or I pop 16-bit data from the stack, where the stack pointer gets incremented by 2. Here is an illustration how basically your stack will work. Now see this. Now this is the snapshot of, or a cross section of the stack, where say 4 locations are full here and these 2 are the empty location. Now which is the top of the stack? As per this picture, the top of the stack is 36674. Now what is the content of SP then? In other words, SP is pointing to 36674. So this is what is the top of the stack. Now after the first push operation, where the data gets pushed, and after pushing the operation, say what will happen is, say SP gets decremented by 2, because for every push operation SP gets decremented, where I am trying to push, say, 2 bytes of data. So there is a new data which gets filled up, so which will sit in 36672. After the second push operation, just for your understanding, now see this, say there is one location or 2 locations empty here. Say after pushing, say another 16 bits of data, say your SP will be, say, loaded with 36670. So the new data, that is the after second push operation, say your SP will point to 36670H. So the top of the stack is, say, 36670H. Similarly, the pop operation works like this, where say now this is the top of the stack, stack is full. So if I try to pop the top of the stack, say the top 2 locations will become empty, say your SP will get, say, incremented by 2. After the first pop operation, your SP will point to 36672. Initially it was pointing to 36670. Now after the second pop operation, carefully observe, after one pop, say your SP gets incremented by 2, say top of the stack will become 36672. After the second pop, your SP gets again incremented by 2, SP will point to 36674H, and the top of the stack is 36674H. Now this is all about how basically your push and pop operations work in 8086. In the next session, let us continue further with how basically the push operation happens, how basically the pop operation happens, and then after discussing about push and pop operation, we shall proceed further with the arithmetic and logical instructions. Thank you.